Alright, let's go ahead and get started. Back on threads. A thread's just a lightweight process. It's actually, there's a couple of tricks to it, but in general, it's just a lighter version of process. Why would we want to have a lighter version of the process?
Efficiency.
Efficiency, yeah, that's very much it. All right, overview. Yeah, we'll talk about different models, different thread libraries, and some examples. But really, you only need to learn about pthreads, because even Windows has pthreads. Because yeah, pthreads is a standard API. Windows is the only operating system that doesn't have native pthread support as of Windows 7. I believe 10 might finally have standard support for it, but there are plenty of packages to just plop it in and start running it. So if you want to work with threads, just use pthreads. It's going to be the simplest way to go about it. A thread is basically thought of as a lightweight process, basic unit of CPU utilization. It has a program counter, a register set, and a stack space. That's all the thread has. But it's sharing with its other threads in the process the code, the data, and any resources. Sometimes it's called a task. So thread and task may be used interchangeably. A heavyweight process is one with one thread, aka a process. Here's a good example. On the left, a single-threaded process, and on the right, it's a multi-threaded process. Notice that the registers and stack of each of the threads are stored in each of the threads while they share code and data. So do you need to do shared memory in threads?
You said you need to do shared memory.
If you want to share data between threads, do you need to set up shared memory?
Yes.
Or is it automatically set up for you is the question?
Oh.
The data could be shared data.
Yeah, it's implicitly shared in threads because it's not copying the data over. You're just sharing the data of the parent process. So when you fork a thread or create a thread, you're implicitly sharing all the data with every other thread that's inside of your process. Again, thread, you just have registers and the thread stack. And then the code is shared, the data is shared, any files that are open are shared, as well as any system resources are shared. Really, it's sharing everything it possibly can. Ooh, another view. So notice you have data and the heap are both shared, but if you have two threads, they would have their own stack, what function they're calling, and maybe local variables as well. But notice the text, by the way, is the program code. Up here you have one thread, stack pointer where he is. Up here you have two threads, thread 1, aka the main thread, with its stack pointer, and thread 2 with his stack and variables. All right, benefits usually are far more responsive than standard processes. You can share resources. Since they're lightweight, they're more economical, so to speak, and they're very scalable because, again, lightweight, and you just keep adding more and more threads. There are a lot of benefits. Threads are what are usually used if you're on a single processor or a single core. Actually, if you're on a single machine, you also do threads, even if they're shared among CPUs. You do not want to try and do threads over Ethernet. That would be very slow. Okay, when you do it, as of writing this book, there were 6 core were available on a chip for pretty cheap. But nowadays, that's going up 12, 16. I forgot, what was the new resin? Was that 32 core?
The AMD thing?
Yeah.
I don't know.
It was either 32, I think it was 32 cores. It might have been 48. But yeah, they're just adding more and more cores. Yeah, I have to look that up. I forgot exactly. There are a ton of challenges in multi-core processing. We're going to get to these as we move on. Hopefully you've experienced at least some of these in architecture. Server architecture. So the client sends a request, the server then forwards it to the thread, and then sends it back to the client. If you're on a single-threaded machine, you'd still do this. The only difference is that, I guess it's not going to show you. You could have multiple threads fork off. And you could choose which thread to send the request. All right. If you have one core and you're running multiple threads, obviously you can't assign one thread to each core because there's 4 threads and only one core. Normally the way this is done is round robin, or at least I should say a common way to do this is round robin. Thread 1, thread 2, thread 3, thread 4, then back to 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Dual core. Maybe core 1 does 1 and 3 and alternates between the two, and core 2 does 2 and 4 and alternates between the two. Can anyone think of why you would want to have one core partition a set threads and not move the threads from one core to another?
Or did you say, why you just want to keep your threads?
Yeah, why does this one go 1 3 1 3 1 3? I mean, we could go 1 3 2 4 1 3 2 4, and this one go 2 4 1 3 2 4 1 3.
So you don't
You would
have to
have
keep
gaps in your processing. I mean, it was easier to manage your time using the same processes.
Well, I mean, it's round robin, so it just moves through. I see what you're trying to say with the scheduler,
Yeah.
but I wouldn't call that big of a problem right now. What were you gonna say, Matt?
It would just make more sense to like have 1 and 3 there and 2 and 4 there.
Yeah,
'cause
from
otherwise
pictorially, yes.
loading them back and forth when you could just,
Why would loading them back and forth be a problem?
because it'd be a waste of time, and you might be able to keep 1 like there in core 1 and work on core 3 or
Core
thread
2.
3. Yeah.
Would it be memory access time?
Right. Why would memory access be better?
Slow you down if you have to go in and out.
What structure is able to take advantage of this? If you have more than one core, why do you want to keep 2 of the threads on that core as opposed to alternating between all 4 of them?
Shared cache thing?
Cache.
Yeah.
Cache is the answer.
I should have just screened cache from the beginning.
Yeah, usually if I ask what performance, blah, 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 the answer is cache. But anyways, right, if up here you have 1 and 3, when you go over here, thread 1's memory is probably still somewhat in the cache, so it can take advantage of that performance-wise and continue on. If you put 2 and 4 back up here, maybe that would blow thread 1's cache out, and then when you got back here, you'd have to reload it again.
Each core has its own cache.
Each core has its own. In general, each core has at least its own L1 cache. And the newest chips, they have their own L1 and L2 cache. All right, user threads. A user thread is managed by a user thread library. It is not managed by the kernel per se, although most of the time the kernel will do something to speed up a user thread. So you have POSIX, Win32, and Java threads. Notice Linux is not on this list. Kernel threads are something that are inside of the kernel, and they're actually realized by the kernel. So that's what, again, Windows, Solaris, Linux, True64 Unix, Mac OS X. All right, guess we'll get to thread. Well, that's the high level of users versus kernel. I think it'll make a little more sense when we get to the pictures. There are different models, because how are you going to map a user thread to a kernel thread? Are you going to map many user threads to one kernel thread? Or are you going to always map one user thread to one kernel thread? That probably makes the most intuitive sense when you're thinking about it. That's what you'd want. Once you create a thread, you'd want the kernel to have that thread and schedule that one thread. But it doesn't have to be that way. Because you could do maybe 4 user threads or actually one kernel thread. That one kernel thread would just round robin each of those user threads. That's still an acceptable way of doing it. And then many, so that's many to one, one to one, and many to many is just mixing it all up. Let's go look at some pictures.
That's not a picture.
That's not a picture. This is just saying that, hey, look, some people actually do many to one, not too many. Here we go. You have many user threads, but there's only one kernel thread, so the kernel is only scheduling this one thread, and that one thread is what round robins through the user threads. Whenever I look at this, I think we're going back to like string theory or something. One-to-one. This is what most people use. Windows, Linux, Solaris 9. Ooh, Solaris. Good old Solaris. Yeah, maps one user thread to a kernel thread, and I think that makes the most sense. You have your user thread, you have your kernel thread. The kernel thread goes on your scheduler and it's able to schedule that thread directly. Many to many. So you can have many user threads mapped to many different kernel threads. Woo! So what that allows is the OS to create as many kernel threads as it wants, is the point of this. Because in the many-to-one, maybe you had one kernel thread and it just figured out what to do. One-to-one, you had any number of kernel threads depending on how many user threads were created. And then many-to-many allows the operating system to determine how many kernel threads it's going to create. Okay, with the thread fiber package. So you have 4 user threads to 3 kernel threads. Why would we do this? That's a great question. Because we can.
Resources?
It's resources. It's that's really the best, easiest way to explain it. The operating system can try and conserve its resources because in the one-to-one, for example, in Linux, I believe a process can only have 256 threads. Why you don't want to have more than 256? I don't know. Just make another process. But anyways, once you hit that 256 mark, the kernel kills your process. In this model, you could have way more user threads, and the operating system is going to stop making kernel threads at some point and just map them over. That gives you a little more capability and a little more flexibility in your programming. What it also allows is that the kernel is then, once it says, okay, no more kernel threads are going to improve performance, it stops creating kernel threads, is the point here. But as you can see, this is probably more complicated. And from what I've read, they say it improves performance, but not by as much as I think they're advertising. But then what do I know? Oh, a 2-level model. So you can, here we go. You can either you can choose to do the many-to-many, or you can choose to do the one-to-one. Cool. All right, thread libraries. Usually there's an API or there's a kernel level support. That's great. Semantics of fork and exec system calls are similar, but you know what? Let's stop and actually do this.